Hello students, welcome to Unit 9 Notes, Section 5.4. This is the last section for your calculus careers, so I hope it is a good one. I'm going to try to keep it as quick as possible. Now, you'll notice that in class we would have used the TI-84 graphing utility calculator, so I'm still going to show you how to do that. Under Math, F9, so if you click the Math key, and you go down to 9, FNINT, it stands for function integration or integral. So you're able to actually, it's going to give you a box here, a box here, a box here, and a box here. So you're going to want to type in your lower limit, your upper limit. You're going to want to type in your function, and then you're going to want to put it in terms of x. Okay. And so for this warm up, you can pause it at this point if you would want to. If you have a graphing utility, you can do that. Okay, or what I also did was on a separate, because of distance learning, I incorporated this slide right here that will allow you to better understand how to do it. You want to go to integralcalculator.net or .com, it doesn't matter, it'll bring you to the same place. And you're going to want to make sure you go to options and change your limits. Pi, you can just type in pi, it knows what pi is, and 2 pi, okay? You type in pi and 2 pi, and then you type in your function, and it should look exactly like this. Okay? And it's going to do the work for you. But I'm going to show you how to actually do these by hand. We're going to stay away from some of them, okay? But other ones that are easy enough to do is what we're going to do today. If you do type in secant squared, type it in as 1 over, let me add that little note. You're going to put in 1 over cosine squared in the calculator. Well, for this one, I think you can type in secant squared and it will do it, but I guess I should change that for the other one. Where is it? Right there. In your graphing utility, you will have to leave it as 1 over cosine squared. For this on the computer, it should work. Okay. Now let's start our our last lesson. So the fundamental theorem of calculus, it truly has two parts, but we're going to focus in on the specific part with a definite integral. So let's go to this right here, the fundamental theorem of calculus part 2. The integral from a to b is of a function with respect to x is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So let me write that. Derivative evaluated at b or the upper limit minus the antiderivative evaluated at a. That's what that stands for. You know what? I will move it. Why do I keep moving it around? Right there. That is what that stands for. Okay? So it's antiderivative evaluated at the upper limit of integration, and then take away the antiderivative evaluated at the lower limit of integration. Okay, so here's our first example. We're going to evaluate this one by hand. So the first thing we're going to do is we're going to find the antiderivative of x cubed plus 1. Remember, you're going to add 1 to the exponent and divide by the exponent. And then we're going to add 1 to the exponent, making it 1x divided by 1. So remember, the derivative of x is 1. The antiderivative is just x. Okay? And now what we're going to do is we're going to evaluate this. We're going to evaluate this from -1 to 3 to 1, or -1 to 3. That's bar notation. That is telling us now how we are going to evaluate it. So this is equivalent to, and you need your bar notation, it's going to help you. So you're going to do x to the third, you're going to do 3 to the fourth power over 4 plus 3. So notice how I took the antiderivative and I evaluated it at my upper limit. And now I'm going to take away literally the same thing. So I'm going to copy and paste it. So you see it's exactly the same. However, it's going to be now at the number 1. So wherever I saw, -1. Whoa, -1, -1. So what I did was I evaluated first I found the antiderivative, which was add 1 to the exponent divided by the exponent for a polynomial. And then 1 is x to the 0, so it really becomes x to the 1 over 1. So it's 1x to the 1 over 1. So it's my antiderivative. And then my bar notation tells the reader how I'm going to evaluate it. So I substitute in 3 wherever I see an x, and then I substitute in -1 wherever I see an x. You can do these separately. You don't have to put it in one long line like I did. You can just do, okay, let me evaluate this at 3 and get an answer. Let me evaluate this at -1 and get an answer. Sometimes that's easier, and we can actually do that. But I want to show you once with it all put together like this. So now this is going to be equal to 3 times 3 is 9, 27, 81/4 plus 3. Take away. You're going to actually have 1/4 because -1 to the 4th is positive. Take away 1. Now, don't forget to distribute your negative. So you're going to get 81/4 plus 3 take away 1/4 plus 1. So we get 80/4, and then 3 plus 1 is 4. So I get 20 plus 4, which is 24. So the answer is the integral from -1 to 3 of x cubed plus 1 dx equals 24. And that's it. Again, if you did these separate off to the side, sometimes it's a little bit easier than putting it all together. But leave everything in forts. Don't try to simplify it if you don't have to. And then, clean up your forts and then clean up your whole numbers. Now, how do I know it's right? Well, for this one, you can check your work. So I'm going to go to the integral calculator because I don't know who has and who does not have at home a graphing utility. Go to options. We're going from -1 to 3. And we are going to go, what was it, -1 to 3, and my function was x cubed plus 1. So x cubed plus 1, x to the third plus 1. Before, just check it over, make sure it looks like what they gave you, okay? Just be careful, sometimes the notation gets messed up, okay? And look at that, there's my antiderivative. Ignore the c because it's definite integral. So we know definitely what it's between. We're not worried about sliding the function up or down, okay? And look at that, 24. There we go. So we got the right answer, okay? If you have an older calculator, you don't need to worry about this. You would use, oh wait, I'm sorry. Okay, well, first off, this is the old calculator notation, which you don't need. You might need it if you have an older calculator at home with older software. Instead of FNINT, they actually use what's called NINT. No idea why, but NINT, what you would do is you would put in your function, comma, the variable, comma, lower limit, comma, upper. So it looks a little bit different versus what FNINT is. It's lower, upper, function, variable. So that goes there, and then upper goes there, and lower goes there, if you have an older calculator. Now, what this slide really intention is what's called total area. The only other focus for today is total area. So, whoops, that's not what I wanted. Total area is important because sometimes if you have a positive area and a negative area, they'll cancel each other out. So, whoops. So you want to make sure that you don't write all over the screen. You want to make sure that you partition it where the zeros occur. So this is the most important part of finding total area. So think about net area. Take all your positive, take all your negative, add them together, okay? With total area, you're going to make sure that you take all the positive area and then you take all the negative area and you think about it in a positive way, and then you add them together. Okay, so if there's some above, some below, they're going to cancel each other out. That's called net. But if you want total, you have to separate them and say, wait, I want this all to be positive. Okay, so you integrate over each of those intervals. So let's do an example. Take a look at this one. You have some positive area here, and you have some negative area here, and they will cancel each other out. So to make sure that they don't cancel each other out, you need to separate this into two different items. So you're going to separate it into 1, 0 to 2 of 4 minus x squared dx. And then you also are going to separate it into 2 to 3 of 4 minus x squared dx. And then you'll add these together. Because look at where that breaks apart, right there at 2. So let's find the antiderivative. You know what? I'll put this here. So we're going to find out what that is. We're going to find out what that is. So I'm going to find the antiderivative, which will be 4x minus x cubed over 3. Okay, and I'm going to integrate that from 0 to 2. And it is literally going to be the same thing here, but it's going to go from 2 to 3. Let's change this one all to blue. We'll keep them separate like that. Okay, so now I'm going to evaluate 4 of 2 minus 2 cubed over 3 take away, you know what? This is all 0. So this is going to be pretty nice. So it's going to be 4 times 0. Don't just make it 0 if you're using a 0, because remember, you might have just a number like plus 5. So you're going to want to make sure you that you check to see that all of these actually do become 0. So we're going to have 8 minus 8 minus 8 thirds, take away 0. So that's good. So I'm going to call this 24 thirds, take away 8 thirds. Wait, 2 times 2 is 4 times 2 is 8. Yep. So I'll get 16 thirds. So that integral is actually equal to 16 thirds. Okay. And this integral here, the nice thing about it is we already did some of the work, because notice we evaluated what we got for f of 2. So we can kind of like cheat off of that information that we have and just pull that when we go to do it. So because we've already done the work for it. So we're going to do 4 times 3 minus 3 cubed over 3, take away 4 times 2 minus 2. I don't like running out of room. Okay. 2 minus 2 cubed over 3. Now this is going to be 12 minus 27 thirds, right? 4 times 3 is 4, 8, 12. Yep, minus 3 times 3 is 9, times 3 is 27. Take away. We already know that this is, we don't need to do work, but it's 16 thirds. So I pulled it from what I had already done. Make sure it's coming from just this, it's not coming from that. So don't always use your end result, but because this was 0, it was good, but always pull from just that piece, not this other one, okay? If you do that, be careful with it. And look at that. So 12, we get 12 minus 9, take away 16 thirds. So we get 3 minus 16 thirds. And I'm going to call that 9 thirds, take away 16 thirds, which is 9, let's see, 9 minus 16. Whoops. 9 minus 16, and you get negative 7, right? Not negative 5, no, negative 7. So negative 7 thirds. So this result is negative 7 thirds. So what we need to do, one last step, is total, find the area total needs to be equal to 16 thirds plus the absolute value of negative 7 thirds. So it's going to be 16 thirds plus 7 thirds. So area total uh, 16, 17, 18, 19, 23 thirds. Okay. So the area total for this is 23 thirds. Now let's go to the calculator and see what it would have done. So what, 16 minus 7? Let's see if we would have gotten 9/3, which is 3. We probably would have gotten 3 for this one. So let's go 0 to 3. We actually already have 3 there, so let's put in 0. The equation is, whoops, the equation is 4 minus x squared. 4 minus x to the 2. Let's see what it gives us. I'm thinking it's going to give us 3 because it's going to wipe it out. Look at that. Boom, it wiped it out. 3. You know why? Because it took our positive area and it added it to our negative area and it cleared itself out. So it did 16/3 take away 7/3. What we want to do is 16 plus 7/3 to get 23/3. So watch what happens when you do this one little thing. Change this to the absolute value and watch what happens. If you absolute value the function, let's see, what did it does not like that. Absolute value of 4 minus x squared. Huh. It did it. Oh. Well, what did we get for an answer? 7 2/3. Let's see. What is 23/3? It's 7 2/3. So equals 7 2/3. So it all worked out. That calculator has a little bit of a problem doing it, but your graphing utility calculator really doesn't mind doing the absolute value. It actually asks you to do that within the theorem. See how it says to find the total area, put this in an absolute value. And then you'll always get total area instead of net area. That's all you have to do for that. Okay? Just like this one. So find the area of the region bounded by the curve. It forces everything to be above the x-axis. It's the same amount of area, but it's just the positive version of it, not the negative version. So our last example, I'll do this one in our calculator. So I'm going to do, let's see, I'm going to set it up like this. -3 to 3 of x cosine of 2x, absolute value, dx. And so I'm going to do it in 2 different locations. I'll do it on my graphing utility because I have the ability to do so. And I have x cosine 2x. I want to make sure my calculator is in radian mode, which it is. And it looks like I get 0. Wait, oh, yep, I got 0 because, hey, take a look. I did the same amount of positive and negative area, so it wiped itself out. Not what I was looking for. I need to put in absolute value. So math, FNINT, -3 to 3. Now I'm going to click math again and go over to number and pick up my absolute value. I'll type in x cosine of 2x and dx, and I now get, I typed it in wrong one more time, -3 to 3. I messed that up. Math again, number, absolute value, x cosine 2x, close parenthesis, dx, we get, well, it takes a long time for it to calculate. It is still thinking. Still thinking. Wow, that took a long time. That was a lot of mathematical operations. It comes out to about 5 5.425 units squared. Okay? 5.425 units squared. Let's try it on here. This will be our last problem, I'm thinking. So -3 to 3. We're going to do the absolute value of x cosine of 2x. Always check it. Looks like I entered it correctly. Give it a second. This could take a while. Oh, you know what? It does not like it at all, one bit, but it gave us an approximation of 5.425. 5.425, 5.425. So both calculators gave me the same result. Okay? So you're going to want to do, your homework starts here. I gave you some derivatives and antiderivatives to work through. Yeah, and I threw some graphs up there. So try your best on these, and let me know if you have any questions. You can book me, and we can also ask me questions during the Google Live. Okay, good luck. Make sure you upload this to Google Classroom.